So good evening to you all. So welcome to this new session. So actually we are running a bit behind of the schedule. So today I will be covering the basics of raster processing because today it is scheduled to be covering. I was supposed to cover vector data processing. So anyway, some things are still I have to complete in raster data processing. So I will just give you a brief overview of raster data processing, and we will continue with vector data processing. So today we'll start with mosaicing images. So what is mosaic? Mosaic is a combination or merge of two or more images. So actually what might be happening, you may have like different images, especially distributed images. So they may be they may be covering different geographic area. So now suppose if you want to make this as a single image and placing that a particular image in its correct geospatial location. So that is called mosaicing. So here you can see that like this proportion of the image is covering this area, and this is covering this area, this is covering this area, and so when we combine these all together, so the images come to their correct geospatial location. So that when we are creating a single image out of these multiple images, so that is called a mosaic. So here you can see that this is a mosaic image of these sub images, and every portion of the image is placed in its correct geospatial location. So for because of the paucity of time, I will be just covering. I was supposed to cover in more detail, but because of time constraints, so I am covering how. I will be covering just a basic command utility for mosaicing a set of images. So for this purpose, we will be using a GDAL utility called GDAL warp. So with the help of GDAL warp, we will create a mosaic image. So actually GDAL warp is quite versatile utility. So after merging the image, actually you can do a lot of things, like you can change the spatial resolution, you can clip the image to certain extents, and so I will be showing like which all multiple options are available with GDAL warp. So here now in my base directory I have some 4 images. So they are covering different geospatial location, and we will combine these all images together to create a mosaic. So like same thing, I will be importing first all the required libraries. So now I have imported the required libraries. So first thing what I am doing, I am just changing my working directory to the directory where my data exists. So this is my base directory like D drive, NNRMS, Haridwar, and mosaics. So I'm just changing with os.change directory. Os.change directory is used for changing the current working directory. So with this, I'm switching over to this directory, or otherwise I have to give the full paths of my file. So in this folder, I have these files band2, then band2 images, but they are covering different geospatial locations. So the extents of these all 4 images are different. So we will combine these 4 images together, creating a single seamless mosaic. So it might happen these images may overlap. So some 2 images might overlap certain areas. So if the 2 images are overlapping together, so GDAL has a disadvantage there, that it will select the last image from your mosaic set. So like in other utilities, like you can select where the overlap areas are overlapping. There you can either calculate mean, max, or some different. But in case of GDAL, it selects the latest file for the overlapping area. So these are my file names. So here what I am doing, I am just reading all these files one by one. So this is I am just reading the data for the file just for visualization. Actually, when you are going to mosaic using GDAL warp, you need not read these files separately. I am just for visualizing these images, I am just reading it. So here what I am doing, I am creating an empty list first. Then I am looping over these file names one by one. Then I'm first just opening the file, and appending the data. I need to read. So then I appending each of this data set to my DS list. So this is done. Then actually for warping the image, quite one single command you need to use. With that, it will mosaic the images all together. So that is gidal.warp. So gidal.warp. Then first argument you need to pass it the name of your destination file. So I am creating a file called mosaicimage.tif. So in this file, my mosaic image will be written. Then the second argument you need to pass a list of file names which you want to mosaic together. So first is your destination file name, then file names. File names will be a list of file names or a list of data sets which you want to mosaic all together. So here anyway we have just the name of files, so you can just pass the name of files as well, or I could have passed this DS list as well. So both options are available. Anyway, I am just passing the names of files. And finally, it will write this data to mosaicimage.tif and return a data set as well. Then anyway, I am writing a format. I am writing this image in a GeoTIFF format. So actually, there, if you want some more options are available, like you can pass on Jidal dot options. So here, suppose in the warp utility, you can like change a different options. Like you can select the format, output bounds. Suppose after the image is created, you just want to clip it to certain regions. Then you can even reproject like output bound SRS in which projection system you are telling. Then a resolution of your image. Like after mosaicing, you can change the resolution as well. Then whether you want to target the aligned pixels, width, height, either you can specify resolution or width and height of your image. Then source SRS. Otherwise, by default, it will take the SRS of your original image or destination SRS. Suppose if you want to reproject the mosaic image to different SRS, then and so on. So there are different options. The sampling algorithm, no data. If you want to set similar in destination, if you want to set any no data, or you want to the program to run as multi-threaded, then you can specify memory callback functions and so on. So once this is done, this will create a mosaic image. So a destination, a mosaic set has been created. And now let us visualize these all together. So what I am doing here, I am creating a figure, and in this every figure, I am just plotting my original data. So if you see, these four were our original images. So similar way, we can plot our mosaic image. So just I need to call dt.imshow. So here I will be passing my destination data set. So dst_ds contains dst_ds is my destination data set in which the mosaic images, just data set of mosaic images. If I run it, so here you can see that this four images have been combined together. Actually, this I will just increase the size of this figure. So here you can see that this portion of the image is on the top here. See, you may be able to see the differences, like when you are changing from one image to image, like this is not quite seamless. So we can make out like, because these all the images have been acquired on different days and different times. So you can see the change in pixel reflectance because these images are all on different time. So here you can see that this way we can combine these all four images together. So you can combine more images and create a mosaic using just by calling a Jidal warp utility. So here you can see this image is covering this bottom left portion, and this is bottom right here, bottom right image. So this way, all four images are combined to get into a mosaic image. So the next thing was like you can calculate some indexes on the image. So that is called local operations. So local operations means you are applying some operation on the individual pixels in all the files together. So that is called local operations, or you can apply some global operations also. So I will not be covering those in much detail. Like for applying local operation, you need to just all the files one by one. And anyway, after reading the file, you will get numpy arrays. And on the numpy arrays, you can apply any of the operations. So with this, I complete my introduction to the raster geoprocessing portion. So now I will be covering the uh, vector data processing. So, so I hope in the first lecture you were introduced to the second vector data model that is called vector data. So I just, for the sake of completion, I will be covering the basics of vector data so that your memory gets refreshed. So what is vector data? So vector data represents objects on the Earth's surface using their latitude and longitude. So any feature can be represented on the Earth's surface using their latitudes and longitudes, or it may be just the latitude or longitude, or maybe a combination of pairs of coordinates, maybe like line, polyline, or polygon. So any feature can be represented either as a point just containing a pair of just containing latitude and longitudes, or a combination of pairs of coordinates. Like you will line will have two endpoints, or it can have, or polyline can have multiple endpoints, or a polygon. So what? So generally, all the features on the surface are represented either using point, line, or polygon. So this is ideal for representing data which has discrete boundaries. Like you want to display a city. So when you are seeing the map of entire India, so every city can be represented using a point. But when you zoom in, so every city will have some boundaries. So then the city can be represented at a polygon. So what is point data? A pair of coordinates, longitude and latitude, that represents the location of points on the Earth's surface. For example, location of a city, or maybe location of a drop boxes for email, or some landmark. Landmarks can be represented as point data. So point will be represented using a pair of coordinates that is called latitude and longitude. So their latitude and longitude on the Earth's surface. So this way, points can be represented. So line, what is line? Line is a series of points that represent a line on the Earth's surface. So for example, maybe we can represent center of a road using a line, or rivers we can represent using lines. So lines will have a series of points. Then third representation is polygon, a series of points that define the outer edge of a region. And finally, the starting and ending point must be the same. So the polygon must be a close figure. So outline of a cities, countries, continents can be represented using polygons. So these images has been taken from the Google Earth. This is the particular link. And the part for GeoPandas, whatever I will be covering, was taken from geopandas.org. So actually there are, either you can use OGR also for reading vector data, but using OGR is a bit difficult. So because we don't have sufficient time, so I will be covering just GeoPandas for reading vector data files. So this here you can see that this is a vector data. So this is showing the map of Uttarakhand, and every tehsil is shown using a polygon. Similarly, all these polygons make the entire Uttarakhand's outer boundary. And plus then we have attached the name also to each of the polygons, like this is called an attribute of our polygon. So for using this, I will just introduce you a basic library called Pandas. So GeoPandas is based on the Pandas. So in this we will learn, I will give a basic introduction to data frame and series. And we'll access and manipulate the data frame and data series and import data into CSV data frame and so on. So Pandas is an open source BSD license library for providing high performance, easy to use data structures and analysis tools for Python programming language. So Pandas is a column oriented data analysis Python library. It's a great tool for handling and analyzing tabular data. So Pandas, there are two primary data structures to be used in Pandas. That is, one is data frame. So data frame you can think of as a relational data table with rows and columns. But what happens here, every row and column will have a name. So column anyway will have name, but with every row also you can attach a name. That is called the index of your row. So data frame is a table, entire table, and series is a single column out of that data frame is called a series. So multiple series when combined together, we create a data frame. So now let us see that how do we create different series and series as well as a data frame. So anyway, here first for import, first you need to install pandas on your system. So then you will like pip, either pip or conda install pandas. You can just install pandas on your system. Once it is done, so then this is the convention generally used for importing pandas. Import pandas as PD. So pandas we will give a short name PD so that we need not type pandas all the time. So import pandas as PD. And I'm just changing my working directory to the vector. In this my vector data is available. So now suppose if you want to create a series means you are creating just a column in your tabular data structure. So series can be created using like NumPy arrays. You are creating np.array and passing it the list of numbers. So similarly here, a series can be created using pd.series and you can pass on the list of elements in that series. So this is a column containing three values. So pd.series. So I'm giving it three names like Dehradun, Almora, and Pithoragarh. So this creates a series. Now, data frame can be data frame objects can be created using a dictionary mapping string column name to their series. So what might happen now? Because data frame will have multiple series, and now we will attach to every series a name. So a name can be attached using like a dictionary. So like here now you can see that. Now how do we create data frame from these series? So now here I have created a city name series. City name is equal to pd.series. So these are the values, and another column I have created population. Population of these, this is some imaginary population of these cities. So 10,000, 20,000, 30,000. So two columns we have created. Now from these two columns, now we want to create a data frame. For that, we need to call the function called pd.dataFrame. So in case of series, we are calling pd.series. Now in case of frame, we have to call pd.dataFrame. Then here we have to call a dictionary mapping. So here we are creating like you can say two columns. This is a dictionary because it is coming inside curly braces. So first column name is city name. On the city name, we are assigning the first series city names, and in the second population column, we are assigning the series population. We have created two panda series, and now with the dictionary mapping, we are just assigning column names to every of these series. So now if I run this code, it becomes like city name and population. So you can see there are and there. So this way we can create a data frame object. Now suppose you have data in your CSV file and you want to read it. So I have a file named stations.csv. In this, actually there are multiple air quality monitoring stations installed across Uttarakhand. You assume that, so their location has been stored in a CSV file. So the CSV file might contain like the name of the station and their latitude and longitudes, like what type of sensor is installed at that location and so on. So this way, so I have a file like this in my folder. I will just show you the file. So here I have a vectors.csv file, stations.csv. So here I have a CSV file like these are multiple columns like station ID, maybe this may be a station ID, station name of the station, latitude and longitude. So this file we will read using pandas. So for first I have created a variable name called file name, and in this I have assigned the name of my file. So for reading a CSV file using pandas, you need to call a function pd dot read underscore CSV. Actually, read underscore CSV takes multiple arguments. So you can read it in the pandas documentation more about this. Like what is these every parameter represents. So anyway, I will not be covering in more detail, and we are just passing it the name of file which we want to read. So pd.read CSV and the name of file stations.csv. So once this is done, then it returns a data frame. So now we can call it using, like, suppose if you want to see some summary of or head if you call, so it will show initial 10 lines of your data frame df.head. And suppose if you are just interested in seeing 15 lines, you can pass another argument like number of lines you want to see. So df.head 15, if you see, it will just show you the 15 lines. If you just give df only, it will print the entire data frame. So similarly, there is a function called tail. So head was there, and tail will return you the tail end of your data frame. So it will be showing last 5 rows of your data is displayed here. Similarly, you can pass another argument like tail 10, tail 15, and so on. Once this is done, now suppose if you want to see the basic statistics on your data frame, so you can call df.describe. So df.describe will return you the basic statistics of your all numerical columns. So actually in this particular data, there were only 2 columns which has numerical values, so latitude and longitude. So with the describe, we can see that there are 152 values, totally 152 counts. The mean latitude is 30, longitude is this, then the standard deviation comes around this. So minimum, this is minimum value, this is maximum value, and 25th percentile is at this number, and so on. So this way, if your table has multiple numerical values, you can get the summarized statistics of your data using by calling df.describe. So anyway, this I have explained only df.head and df.tail. So now let us see that how do we access some particular column, or like we are indexing in NumPy arrays and so on. So similarly, we can access individual elements of your data frame as well. Now suppose if you are interested in only accessing some particular column, so what you can do, df your data frame name, then in the square brackets the name of your column which you want to just access. So suppose if I am interested only in accessing the station ID column, so I can just pass df station ID, it returns me the station ID column only. And suppose then this station ID will be a series it returns. So suppose if I am interested in the second second value, so second index also I can pass, like out of this I want the entry at the this index. So then even I can pass station ID into, it returns me this 48906. And similarly, like you are using slicing, so slicing also can be done on the data series. So station ID 4,8, the station ID 4th to 8th row. So this way you can represent 4th, or suppose if you are interested in only extracting the row where the station ID is equal to Haridwar, so you can write it this way, like df, then inside a square bracket df station is equal to Haridwar, or any other conditional statement you can write inside this outer square bracket. So what it returns, this df dot station is equal to Haridwar will return you a series containing whether Boolean series of true or false. So from this we are extracting only the values rows where df is true. So this way you can extract any conditional statement you can return right here. So Haridwar, Dehradun, or So Dehradun, nothing is there. So maybe I think because this is a case sensitive. So Dehradun is not there. So similar way you can manipulate the data. Now suppose if you want to calculate, so latitude she's seeing latitude is shown is in degrees. Now suppose if you want to convert it into the minutes, so you want to add a new column to your table and you want to just do some calculation on one of your existing columns. So what you can do, like df your original data frame and the new name of the new column, like which column you want to add. Like here I want to create a new column with name latitude in minutes. In that I want to store the values of the existing df latitude, and I just want to multiply it by 60. So degrees, if I multiply it by 60, I will get latitude in minutes. So now if I run this df, it returns this. So I'm just clearing the output. So this way you can manipulate any of the column as well, like df latitude in minutes. So df, if I run, you can see that earlier df was not having this column latitude in minutes. Now this has one additional column named latitude in minutes. So now indexes, what are the indexes? Both series and data frame objects also define an index property that assigns identifier values to each series item. So generally what you see that every column we give a name, but suppose if you want to give every row also a name, so that is called an index. So indexing means index is a property that assigns an identifier value to each of the series item or data. So if you assign names to rows as well. So now if you want to index any of the element, now you need not remember the integer indexes. Just by their string representation, you can access any value. So suppose if I want to extract like df station id dot index, if I want to do, now we have to, because this is we have given them integer indices. So the indices you can assign them string also. So it is showing range index starting from 0 to 152. Similar with, now suppose if you want to reindex, like you want to rearrange the rows, so just you want to reindex 2, 0 and 1. So this way you can just reindex as well. Now if you see df, so your output will be shown in this order 0. So by default it will show 0, 1 and 2. Now by reindexing you can rearrange your rows as you wish. So second row will come first 0 and first index will come at the third place. Now similar way, suppose if you want to sort your data frame, so there is a function called df.sort values. So data frame dot sort values, then by which attribute you want to sort it. Suppose if you want to sort it by latitude, you can sort it by equal to latitude. You pass it though, so all the values in your data frame will be sorted based on the latitude value. So here you can see latitude is in, by default it is in a descending order. So if you pass like another descending is equal to true or false, then you can arrange them, or ascending is equal to so latitude are in ascending order. So if you pass latitude ascending is equal to false, then it will be arranged in descending order. So similarly, you can sort it using like multiple column also. Like if two values are, there is a type, then based on the second column you can arrange them. So this way you can pass multiple values to this by parameter as well. So this was the basic introduction to Pandas. So Pandas has basically two data structures: data frame and data series. So series is individual column, and when multiple series are combined together, we create a data frame. So any element on the data frame can be accessed either using integer indices or their string equivalent indices. So now we will cover the GeoPandas for vector data processing. Now, so in this we will cover, there is an equivalent of data frame in GeoPandas is geo data frame, and equivalent of series is geo series. So a geo data frame is like when you read a shape file, you will get a geo data frame. and every column will data series file will have multiple attributes. So every column is a geo series. Then we will cover access and manipulate data with geo data frame and geo series. We will learn how to read vector data, manipulating some vector data, and we will cover some basic processing on that vector data, and we will see how do we write back the vector data. Okay, so GeoPandas is an open source project to make working with geospatial data in Python easier. GeoPanda extends the data types used by pandas. So to allow spatial operations. So Pandas doesn't allow spatial operations. So GeoPandas is the extension of pandas for allowing spatial operations. So anyway, GeoSeries is equivalent of GSeries in Panda. GeoSeries is essentially a vector where each entry in the vector is a set of shapes corresponding to one observation. So GeoSeries will have your actual geometry. So every entry in the vector is a set of shapes corresponding to one observation. Now suppose the file I have shown you like location of different air quality monitoring stations. So every entry in the GeoSeries, now out of these multiple columns, we will create a GeoSeries column. So every entry in the GeoSeries will be a point feature. So GeoPandas basically has three classes for geometric objects: point or multi-point, line, multi-line, polygon or multi-polygon. So GeoSeries is a column, and that every entry or what you call every row in that column is a feature. So that may be a point, line or polygon. So geo data frame is a tabular data structure that contains a geo series. So geo data frame can have multiple geo series, but out of these all geo series, there will be a special geo series that holds the geometry. So that is called the geometry column or geometry of your data frame. So there can be multiple geo series, but there will be a special geo series that will be treated as the geometry of your data frame. So I will be covering this. Now let us see how do we read. Let's first explain about a little bit about vector data format. So vector data can be stored in multiple formats. So ESRI shape file is one of the most popular format for storing vector data. So ESRI shape file is a simple non-topological format. So in a shape file, we cannot store topology. This is a non-topological format for storing geometric location and attribute information of geographic features. So the shapefile format defines the geometry and attribute of geographically referenced features in 3 or more files. Okay, so in the shapefile, all the geometries and attributes of those uh, features are stored in 3 or more files. So generally at least 3 files are compulsory, but some cases you will see more files also. So whenever you download a shapefile, it will have these associated files. So if you are going to open this file in some ArcGIS, QGIS, or any other GIS software, so you will need all these five files. Otherwise, if any one of them is missing, you will not be able to open that file. So the first file will be .ssp. So this is the main file that stores the feature geometry. This file stores the feature geometry, whether your every observation is a line, point, or polygon, whatever may be. Then another file that is with the extension .shx. So this is the index file that stores the indexes of the feature geometry. So this stores the indexes. Then .dbf file, this is the database table that stores the attribute information. So with every feature, you will store some attributes also. So those attributes are stored in the .dbf file. Then SB and SBX, these files store the spatial indexes. So SHX was the index file, and SBN and SBX, SHX contain the spatial index. Similarly, .prj, this file stores the coordinate or projection information attached to your shape file. Then another popular format is GeoJSON. So GeoJSON is the extension of JSON for geographical data. So actually in JSON, if you know, JSON data is stored using key value pairs. So same thing is in GeoJSON also, but GeoJSON you can store point like here. You will store it using key value pairs only. So the first type will be like type. So type, whether type may be a feature or feature collection. So feature Then you have to store geometry also. In geometry again is a dictionary. So here type, coordinates. So this is a feature. When you attach some attribute, you can attach some attribute also to your feature. So by using properties key. So properties with using like properties key. So suppose we are storing it as a point. So anyway, here using type is equal to feature, and in geometry key we are storing type, it is point, and these are the coordinates. Similar way you can define type, polygon, and the pair of coordinates. Similar way, then you can properties or attributes of your feature you can define using properties key. So properties then inside under dictionary like name, some location or any other attribute like temperature and whatever is required for your feature. So those attributes can be defined using properties tag. So then there are other formats, like these are two of the most popular, shapefile and GeoJSON. Geographic markup language or GML or KML, keyhole markup language, MongoDB, Microsoft SQL Server spatial database, OGC WFS services, and so on. So the vector data can be stored in these different formats. Now let us see how do we read a shapefile. So right here I have a shapefile. I will be just showing you the shapefile. I will open it first in ArcGIS. Then we will read the same file using Python. So it takes a bit of time. So anyway, by the time I will show you, like first you need to install GeoPandas. So whether you can use Conda install GeoPandas. So then we are importing GeoPandas like pandas. This was a condition for pandas. We were using import pandas at PD. So GeoPandas I will write as GeoPandas at GPD. Then NumPy, pandas, and matplotlib for just for visualization. And GeoPanda, from GeoPanda we can import like GeoSeries, GeoDataFrame and GeoSeries. So here I have a vector file called India state boundaries. So in this shapefile I have the state boundaries of India. So I will just be showing this file in first in ArcGIS as well. Then we will see how to read it using GeoPandas. So my ArcGIS is taking a bit of time. So please hold on. So anyway, this is taking a bit of time. So otherwise, by the time it opens, we will cover the remaining portion. So for reading the file, anyway, I have created a variable here called vector file. So vector file, in the file, I have stored the name of my file .ssp. And now for reading the file like pandas pd.read csv, geopandas.read underscore file. If you call this function, it will return you a geodata frame. So gpd.read underscore file and pass it the name of file, shape file which you want to read. So India equal to gpd.read. So this reads a vector file and returns me a geodata frame. Now if I inspect India, you can see that it will showing the district like this India. So this is showing length, area. So these two attributes have been stored there, and this is the geometry column, and this the geometry column stores polygon or multi polygons. Now it has opened. Now let us save it. So here I have India state boundary. So I will open this boundary.shp file. So this is my shape file. Now if I see the attribute table attached here, I can just right click here and open attribute table. So attribute table here you can see that shape length and shape area, two attributes only are there. So same attributes you are getting here also, shape length and shape area, and the geometry column. Geometry column is a feature like shapes of or every feature. So this way we can, like, just by calling gpd.read_file and passing it the name of your shape file, you can get the read the shape file. Now similarly, like you want to know what is the name of your geometry column. So you can call your geodata frame. Like if I print the type of India, it will show the geodata frame. So geodata frame. Now suppose if you want to know the name of a geometry column, you can just call geometry.name. So it returns the column of the name of the geo series is geometry. So it has written geometry. Now suppose if you want to query what is the projection system or CRS used in your file, you just can call geodata_frame.crs. So it returns you the CRS of your file. So this data is stored in geographic EPSG 4326 geographic coordinate system WGS 84, and so this is the detail of our coordinate system attached to our file. Now similarly, now suppose if you want to change the name of any column, so geometry column, instead of geometry column you want to change to the name borders. So you can just call your, these functions are available in pandas also, data frame dot rename, and like you want to rename the columns. So columns, then you need to pass a geometry, pass a dictionary. So dictionary will contain old name and new name. So geometry, now you want to convert it to borders name, and now the borders column must be the new geometry of your geodata frame. So then dot set geometry equal to borders. If you do, then if I run india.head, you can see that the name of geometry column has changed to borders and it has become the new geometry of our data frame. Now suppose if you want to visualize it, so visualization means the geometry column only will be drawn. So all the polygons or multi-polygons in this particular column will be displayed. Now suppose if you want to plot it, so we can just call a plot function on our data frame dot plot, and inside this we can pass figure size. So if I don't pass a figure size, you will see a small figure. So this way you can visualize your, so all the polygons have been drawn here. Then if you want to change it bigger size, so this way you can plot. So you can visualize your vector data by calling just your geodata frame dot plot function. Similarly, what happens? Generally, what happens? You will get the shape file in a zip file. In the zip file, all your associated files will be all together. So you need to extract those files, then read the shape file. So instead of that, actually directly you can read a zip file as well. For reading the zip file, what you need to do? So your file name, you need to put it like this. Vector file is equal to zip colon and double slash, then the name of your file. So in this case, what will happen? Directly zip file can be read. You need not extract the individual file and read the shape file. So vector file also you can directly read it like this. gpd.read file. Now you need to pass the vector file. So anyway, this is the same thing. Now I'm plotting it. The same file I can read it using the file. Now this is the file is district boundaries. So now you are seeing more polygons in this file. So earlier previous file was the showing the state boundaries. This file is showing the district boundary. So this way you can read a zip file also directly. Now let us see that how do we subset a geodata frame. Now because now you have extracted the entire India. Now suppose you are interested only in the state of Karnataka. So this way you can subset the file also, like raster we were subsetting. So now here just I want to know if you see here India, it has attributes like so in this particular district boundary save file, every feature has an attached attribute called name1. So name1 I think is containing the name of the state. So now suppose if you are interested only, if you are out of these all features, you are interested only in extracting the boundary of Karnataka state. So then you can do like this name1 attribute contains the name of the state. So you can just call like subset equal to India. And like we showed in the previous example, India, then name of our attribute, which attribute we are looking for. India name1 is equal to Karnataka. It will just return us the boundary of Karnataka, all districts in Karnataka, boundary of all districts in Karnataka state. So you can see now if I plot it, subset dot plot, you can see that the district boundaries of Karnataka state has been extracted. So this then you can close. Now suppose if your shape file is too large, so instead of after first reading and then subsetting the image, you are interested just in reading just a subset of your data. So that also can be done like, so first you need to define your bounding boxes. Bounding boxes will be in the form of minimum longitude, then minimum latitude, max, or you can say that min x, min y, max x, and max y. So this min x, min y, max x, and max y. This way you have to define your bounding box using 4 item tuple: min x, min y, max x, and max y. And when you are reading gpd.read underscore file, geopandas.read file, then you need to just pass another argument called bounding box. So these this covers the state of Uttarakhand. So if now if I see this UK and bounding box, and if I run uk.plot, now you will see that almost this area of Uttarakhand has been extracted. So instead of reading the entire file, only we have read the features in this geographic location, like from starting from 77.57 to 81 point something and 30.28.72 to 31.5. This way you can just read a subset of your whole file as well. Now similar way, suppose if you have a GeoJSON file, GeoJSON file also can be read in the similar fashion. Now I have a Tehsil Almora Tehsil.geojson file which contains the boundary of Almora. So I can read this file using this. I have defined a variable, then gpd.read file and passes the name of GeoJSON file. So any format can be read using the same function called read file. So this, if I plot it, then now suppose if I want to attach an attribute as a label to each of these polygons, that also can be done easily using matplotlib. So here you can see that we have attached an attribute to each of these polygons as well. Now let us see how do we write a shapefile. So anyway, Almora, if you see Almora, this is our Almora geodata frame, and this has different attributes like tehsil, district, and geometry. Now I am attaching a more column to this, like some imaginary population of these every tehsil. So population equal to this. Now I have created a series with population name. Now I just attach this to the Almora. So in Almora, I am creating a new column with name population. In that I am storing the value of this population. Now if I see the Almora, a new column with population name got stored. Now I have a geodata frame. I have a geodata frame with 3 attribute series and a geometry column. So this is the geo series. This is the geometrical. These also can be geo series, but this is a special geo series containing this is the geometry. Now for writing the file to shape file, now if I see here, more I will delete. So now here you can see that there are some files. I will just delete these files like this. Now if you just write almora.to underscore file and give it the name of file almora.shp, you will see that all these files will be created here. So now you can see that these almora.cpg, dbf, prj, shp, and shx. These files got created here automatically. So now these files you can either read using GeoPandas or using any GIS software as well. So this way we can write a shape file. Similarly, suppose if you want to write it into a GeoJSON format, you have the data frame and you want to write it in GeoJSON format. So same function you can call to_file, and here the second argument you need to pass driver. So by default driver takes a ESRI shape file. But if you want to write it in GeoJSON, you can just pass driver is equal to GeoJSON. So here almora.geojson file will be created. Almora.geojson. If you open this file, in this you will see like these are type feature collections. This is CRS. Then these are the features like features, properties, tehsils, almora district, almora population. And this whatever attributes we attach to it. And then geometry is type, polygon. These are the coordinates of that geometry and so on. So this way you can, the single command you can shape in any of the format of your requirement. Now let us see how do we create maps using GeoPandas. Anyway, now we will read the same file. So the same function plot. So plot we will use for visualizing it. In Uttarakhand, I am just reading gpd.read file, and this vector file I am assigning it to the variable vector file. I have read. Now Uttarakhand.head, if I see that this is showing the tehsil boundaries of different Uttarakhand. Now suppose if you are call Uttarakhand.plot and don't pass it any argument, so it will be showing the polygons in a default color scheme. Now suppose if I want to change this color to green, so I can pass the argument color equal to green. So the it will be filled with green color. Similarly, you can change edge colors, fill colors, so different attributes are there, you can change. Now suppose I attach a population column to this, then Uttarakhand population equal to population. So now suppose if I see Uttarakhand.head, now see that there is a population column also attached. Now suppose if you want to create a choroplast map of this based on the population, so you want to color these polygons based on the value of population in that polygon or in that tehsil, so that you can choroplast map also can be created quite easily. Like you can call Uttarakhand.plot, then there you write column on which column you want to create a choroplast map. So here I want to create a choroplast map based on the population. So if you will see that the colors of these polygons have been the color have been assigned based on the value of the population in that particular polygon or tehsil. Now anyway, now we are not seeing any legend attached to this plot, because just by color we don't know what this color represents which number and so on. Suppose if you want to attach a legend, so you can pass another argument to your plot function, column is equal to population, and legend, if you pass legend equal to true, then it will attach a legend also to this map. So here you see a legend as well. Similarly, suppose if you want to create a horizontal legend's orientation also can be changed, like by passing legend keywords, label and orientation. Orientation equal to also another dictionary you need to pass legend keywords, figure size. So now if you see that the the label also attached to the legend, and it has been in horizontal orientation. So similarly, now suppose if you want to change the color map, instead of this default color scheme, you want to use a different color scheme. So then there are, you can pass a CMap argument also, color map. Then this way it will change the color scheme of your population as well. Similarly, now suppose this has broken the total entire population in a equal interval scheme. So every 10,000 it has created a new color. So those break also can be done. Like suppose if you want to break the total population using natural breaks or some different breaking scheme, you can use those things like head tail breaks, Fisher Jenks or something. So you can just call Uttarakhand.plot and scheme. So this will be the for manipulating the scale, you can pass the scheme. So natural break, suppose if you want to pass, you can pass scheme equal to natural break or Fisher-Jenks, whatever, whichever way you want to break your entire population. That way you can break and make the color scheme. So it takes a bit of time. So this way now you can see that instead of default these numbers, now the population has been, this looks a bit better, and the population is arranged or broken in by using natural breaks. So this was the single part. Now similar way you can add multiple layers to your plot as well. So now suppose same thing before combining maps. So first you need to, suppose now you want to display multiple layers, like you have a base. You can assume that you have the boundaries of all tehsils, and you have a, that is you have as a polygon layer, and the second layer you have the headquarters of those tehsils or districts. So that may be a point layer. Now suppose if you want to visualize those together, so first requirement is that the projection system of both must be same. If they will not, if the projection system of the both the files will not be same, they will not align properly. So let us do that. How do we create a multi-layer map? So first I am reading the Uttarakhand file. So Uttarakhand.shape file directly anyway I have read. Now I am just creating imaginary headquarter of each of these tehsils. I am just copying this original file. So so then actually if I see my Uttarakhand dot, so this is in EPSC 4326. So temporarily what I am doing, I am just copying the Uttarakhand to headquarters also. Then I am just reprojecting it to EPSC 3395. Then so I am at tehsil headquarters equal to tehsil. So what I am doing here, tehsil headquarters. So I am creating a new column by name tehsil headquarters HQ. So in that what I am assigning, I am calculating centroid of each of these polygons. So centroid of each of these polygons will be a point. So I am calculating first here centroid of each of these polygons and assigning it to a column called tehsil headquarters. So now if I see tehsil HQs, so you can see the new column with point geometry got created. So how do we calculate it? We calculated the centroid of each of these polygons and assigned it to a new column. So this way we are assuming an imaginary headquarter of these tehsil in this particular location. So now this, because now by default this is the geometry of now this particular geodata frame contains two series. Now we want to make HQ as the geometry of our column, so that whenever we plot it, this tehsil HQ is drawn as a point geometry. Now so that I can call using tehsil headquarters equal to tehsil dot set geometry is HQ. So then I am just dropping the column geometry column. Now if I plot it, so here you can see that this has plotted as a point feature. So now because this we have converted to EPSC 3395. So similarly now, because now when we want to create a multi-layer map, we need to convert our Uttarakhand map also to this. So for reprojecting the map, we need to just call 2_CRS. 2_CRS, then to which EPSC 3395. Now if I plot, so this is the plot of Uttarakhand. Now you can see that this is the EPSC 3395 projection system. This is the boundary of tehsils, and this is the location of headquarters of every tehsil. Now suppose if you want to visualize these two plots together, so what you can do, first we can call like plt.subplots. So plt.subplots creates a figure and an axis. Axis is the area where chart is drawn. So first thing you need to create your base plot. So base plot, suppose if you want to, the boundaries of these tehsils we want to be plotted as the base plot. So here we are calling Uttarakhand dot plot on this axis, ax is equal to x and color equal to white. So fill color we want to bring it white and edge color black. And the second tehsil headquarters dot plot, and in this axis will be same or ax, then markers anyway, every point you want to show as O and color red and marker size. So first you need to create a subplot, plt.subplot will return you an axis, and Uttarakhand.plot, in that you just need to first your base plot, then in that ax, then to your second layer, also you need to pass axis object as your created axis object. So first this axis will be drawn on this empty axis, Uttarakhand will be drawn on this empty axis. Now on this Uttarakhand axis, this headquarters plot will be plotted. So now if you see that, this way we have created a multi-layer plot. So this is, once you close, then you can delete all these files. So now let's see that how do we manage projections. So GeoPandas accepts a lot of representation, like Jidal was taking, we saw that there were multiple ways to represent a projection system like PROJ4 string or WKT, WKB. So similar way, GeoPandas accepts representation of CRS in PROJ4, or directly you can write in a dictionary format also, like projection, ellipsoid, datum, and so on, or EGPS code also you can define. So for setting the projection of your geometry, you can just like, you can just call 2_CRS method. So 2_ and we have seen previously as well. Just 2_CRS, either you can attach a projection or an existing projection system, you can reproject to different projection system. So like here I have using, so this is in 4326. Now if I change it to EPSG 301, just I can call Uttarakhand.2_CRS and go by just calling 2_CRS, and I can reproject the image to a different projection system. So here you can see that these are two different, one was in WGS84 and this is Mercator projection. So here the values are in latitude and longitudes, and here these values are in meters. This is a projected coordinate system. So now let us see how a basic geospatial analysis. So for there are multiple features. So for every feature, you can calculate the area, bounds of that feature by calling length, geometry type, and so on. So suppose if you want to create a point geometry, so a point geometry can be created using from Shapely. Actually, Pandas uses another library called Shapely. So Shapely.geometry, you can just create a point and give it coordinates. And suppose if you want to know the geometry type, point, and area, if you want to give it for the area of the point will be 0, and length also will be 0, and bounds, you can get the bounds of your point. Similar way you can define line or line string. So in case of line string, you need to define the multiple endpoints of your line. So then you can calculate the area, length, bounds, or coordinates of your. Similar way you can define polygons. So actually, as I explained that what should happen, your starting and ending point, ending vertices of your polygon must be same. So when you are creating a polygon object and you are not creating your end vertex as your starting point, so what will done? So Shapely by automatically will assign implicitly close this graph. So here actually though we have created 3 points only, but it has connected those. Or either you can explicitly close also. Here you can see that last endpoint also we have defined as 0, 0 only. So these both will be same. So the similar way you can calculate length, area, bounds, or you can combine multiple, you can draw a buffer around a polygon like this. So you can draw a buffer. You can combine them together and so on. Or suppose if you want to calculate, you want to visualize the convex hull. So convex hulls also can be like here we just read Uttarakhand 5. Now suppose if you see, now suppose if you want to create a convex hull, a smallest convex polygon containing all the points in the object. So that is called the convex hull. So represents returns a representation of the smallest convex polygon containing all the points in this particular object. So that is called the convex hull. Suppose for this entire geoseries, if you want to calculate convex hull, you can just call CH, we will call it Uttarakhand dot convex hull. So it will represent you a convex hull. So if I plot it, you can see that this is the smallest convex representation of this complex feature. Similarly, suppose if you want to draw an envelope around this, you can just call data frame dot envelope. Then it draws an envelope around this. Suppose if you want to simplify, simplify returns a simplified representation of the geometric object. All points in the simplified object will be within the tolerance distance of the original geometry. So if you have a very complex geometry and you want to simplify it, so then you can just call dot simplify, your geodata frame dot simplify. So now you can see that this is the simplified representation of this geometry. Or then you can call unary union also. So this is really a union of all your objects. So this will be finally represented as a single geometry. So all this geometry will be merged into a single geometry. So by using the operation unary union. So once and this takes a bit of time. Now if I see it, you can see the plot as a so you can see a unary union. Now let us see. Now we'll see that how do we create a geodata frame from a CSV file. So for example, suppose the CSV file which I have shown you, it contains the location of multiple air quality monitoring stations across Uttarakhand. Now this you have in a CSV file. Now suppose if you want to visualize them geospatially, just by reading a CSV file, you will not be able to visualize where the locations are there, how the distribution, how their geospatial distribution is there. So for that and visualizing them, you need to convert it to a geospatial format. So now we will see that how do we convert a CSV file to a geodata frame. So here anyway, I have defined my variable name called file name is my stations.csv. So first I am just reading that file using pandas. So now if I see this file has like these attributes: station ID, station, and name of the station, latitude and longitude or position of that station. Now what I need to do, I need to create a point geometry by combining these latitudes and longitudes so that I can visualize it. So for that, what I need to do, I need to create a geoseries. A geoseries will be like by combining this latitude and longitudes, I will create a new point geometry here. By combining these two, I will create a new point geometry here. By combining these two, I will create a new point geometry here. So for that, what I need to do in pandas, there is a function called points from xy. So there is a function points from xy which converts, if you give it 2 points, it will convert these points to a point geometry. So what here we are doing, gpd dot points from xy and df dot latitude. So df dot latitude, if you see, it returns us this entire column. So sorry, this is capital L. So df dot latitude returns this entire column. The similarly df dot longitude returns this longitude column. Now gpd dot points from xy, if you pass it to different geoseries, what will it will combine these two and create a point geometry. Combine these two for and create a new point geometry. So this way, this will create a new column here or new geoseries, and every element of that will be a point feature by combining the latitude and longitude value of the corresponding row. So now if I run this, and if I run geom.column, now here you can see that it has created a point geometry. Like first point is combination of this 77.86 and 30 points. So first is longitude X and second is latitude 77.86 and 30.70, then 78.07 and 30.73. So this way you can convert two points or floating point numbers to a point geometry. So we have created a geometry column. Now what we will do, we will create a data frame. So gpd.geo data frame. So we can pass it different arguments like from which data frame, a pandas data frame. We need to pass it first gpd.geo data frame, a pandas data frame, and which column you want to make as a geometry. So what we are doing here, geometry is equal to as geo column. So one new geo series we are passing it, and that we are assigning as the geometry of our geo data frame. So now if you see this geo data frame, now you can see that a new column with geometry name got created here. And these are available, station ID, name, and these attributes remain same, and the new geometry column got created. So for creating a geo data frame, gpd.geo data frame, then your first df, that will be your attribute geo data frame, and a column which contains the geometry of all of your features. So here we have geometry equal to second geo series we have passed here, geometry column. Now if we plot it, so you can see that this is the description of this. So now suppose if you want to write it to a shape file, so first thing we need to attach a EPSC or projection system to this. Otherwise, if you open this file with any other GIS software, it will complain that special information or special projection information is missing, so it cannot project it on the map. So like we explained in set CRS function, by calling set CRS function, we can attach the projection system to it. So GDF equal to ZDF.setCRS, then EPSD 436. Then we can write this file to a shape file like CSV file.shp. So this way we can convert any CSV file to a shape file. So this was all about today's lecture. So if you have any question, you can post it. So thank you very much for attending today's session.